Hello, my name is Jacob Teigen, and today I'm going to be talking to you about the research I conducted with Concordia during the summer of 2020. I conducted this with the chemistry department here, and my advisor was Dr. Donald Krogstad. A little bit about myself. I'm currently a junior here at Concordia. I'm a biology and a chemistry major, and I'm looking to go to medical school. Today, I'm going to be talking to you about the development of a synthesis protocol for ligand-targeted chemotherapy using cisplatin and folate. I apologize as that title's kind of a mouthful, and it may seem overly complicated, but hopefully I'll be able to break down the details in a pretty simple way, as it's a very interesting topic, at least to me, and I think it has a lot of good applications in today's society. With some background information into my topic, I'm going to first start with something that I think most people are familiar with, and that is cancer. Cancer is currently the second leading cause of death in the United States, and cancer is essentially a disease of your own cells. It occurs when cells in your body begin to mutate and they divide irregularly. Some divide very rapidly, and others divide faster, but not necessarily at an extent that's going to cause extreme issues. And this is kind of where you get the variable stages of cancer and aggressiveness. So obviously that this is a very applicable disease, there's going to be a multitude of different treatments that are developed. One of the most common treatments that's applied in different patients is known as chemotherapy. Today, the drug I'm going to be talking about, specifically the chemotherapy drug, is cisplatin. Now, cisplatin works by binding to DNA and particularly rapidly dividing cells. And it binds to DNA and causes an inhibition of replication and transcription. This leads to the cell no longer being able to do the necessary processes to divide, so it dies. And this coordinated death is called apoptosis. So if you hear that term, apoptosis merely just means coordinated cell death. And in this process of a chemotherapy drug attacking these rapidly dividing cells, it can't differentiate between cancer cells and healthy cells. This causes a multitude of issues because many healthy cells within the human body divide relatively rapidly. These include the cells lining the intestinal tract, hair follicles, skin, nails, and the attacking of this chemotherapy drug on these rapidly dividing healthy cells is what causes the many side effects you see in chemo patients. These side effects are extremely detrimental because these people are battling a horrific disease and they have to face even more obstacles. So essentially, the goal of this research is to attach something to the chemotherapy drug that guides it specifically to the cancer cells. And that's where the term ligand-targeted chemotherapy comes from. The ligand is essentially the guide molecule. And in this instance, we're going to be using folate for the ligand, and cisplatin is the chemotherapy drug. And you may wonder, well, why folate? Folate is essential for cells to build DNA and RNA. And as you can imagine, a rapidly dividing cell is going to need a lot of folate to continue producing its DNA and RNA supply for cell division. To get folate into the cell, however, that's not always an easy process that can happen naturally. So these cells need different mechanisms for bringing folate into the cell itself. Some of these mechanisms include reduced folate carriers, as well as proton-coupled folate transporters. These sound relatively complex, but the mechanism of their action is not really pertinent to this research. But the third method of bringing folate in is, and this is referred to as folate receptors. Humans have 4 of these folate receptors, and they're referred to as folate receptor alpha, beta, sigma, and gamma. The receptor that we researched in this was folate receptor alpha. And the reason for that is folate receptor alpha is overexpressed in a multitude of epithelial cancers. And epithelial cells are merely just the cells that line certain structures within the body. So the colon and the intestinal tract, things like the stomach, breast cancer. So you see this folate receptor alpha overexpressed in many of these epithelial cancers. Not only is it overexpressed, but in cancer cells, it also faces the folate receptor alpha faces out into the bloodstream. This means that there's what's circulating through the blood readily has access to this receptor. In healthy cells, you don't see folate receptor alpha exposed to the bloodstream, which is very interesting because the delivery of chemotherapy drugs is often through the bloodstream, meaning that this could provide an injection of the chemotherapy drug guided by an attached folate to the cisplatin drug that delivers it specifically to the folate alpha receptor shown by cancer cells. So essentially, the basis of this project is to form a ligand-targeted chemotherapy drug by combining folate and cisplatin. And you may say, well, how about the other two mechanisms of bringing folate into the cell? Would that not also work for this drug that you're trying to produce? And it actually does not, because the bulky structure produced by the synthesis reaction of folate and cisplatin being attached cannot be brought in by those two other mechanisms I mentioned, because they specifically recognize folate. And when you add it to another thing such as cisplatin, it can no longer have the machinery to recognize and bring it into a cell. So it really relies on the folate receptor alpha for entrance into the cell. Now, folate receptor alpha is also, it metastasizes cancer cells because it can also act as a transcription factor, enhancing many oncogenes or cancer promoting genes in the cell. So these reasons are kind of why we chose folate as a ligand, as a target for this folate receptor alpha. So the goal, as I've previously mentioned, was to make a ligand-targeted chemotherapy drug using cisplatin and folate. And in this process, it was kind of a two-pronged approach. I was trying to make an amide link, which essentially means I was trying to attach folate to cisplatin using an amide linkage, which an amide essentially means a carbon double bonded to an oxygen, bonded, that same carbon is bonded to another nitrogen. And onto that nitrogen is the folate, or the PTA molecule. So that's the bond that's attaching these two structures. Another student who was working with me was working on an ester linkage, which is the exact same layout, but instead of that nitrogen, it's an oxygen. And this is important because a nitrogen is readily hydrolyzed or broken apart by water, or is not readily hydrolyzed or broken apart by water, whereas an ester linkage is broken apart. So the amide linkage could be used to stick into that receptor and maintain that bond so it's not broken apart. And this is important because it could be used to image by attaching, instead of cisplatin, you could attach a radioactive label or fluorescing label to show where these overexpressing folate receptor alpha are, which shows where the cancer cells are. And then using the other student I was working with, who's making the ester linkage, could deliver that drug, as the ester could be broken apart upon entrance into the cell and deliver that chemotherapy drug selectively to the cancer cells. So kind of a two-pronged approach, and I'm personally working on the first one I described, or the amide linkage. The hypothesis was developed using previous literature that had showed the success of these reactions, and that we could produce these reactions successfully using different reactants and strategies. So the first reaction that was conducted was 4-nitrobenzyl chloride combined with PTA. And I'm going to scroll up here to show you better what that means. 4-nitrobenzyl chloride sounds intimidating, but it really is just referring to this structure right here. This is the product of the first reaction. So on this left side here, this is the 4-nitrobenzyl chloride, and over here is PTA. PTA is referred to as a linker molecule, and it has this cage-like structure with 3 nitrogens and a phosphorus up top. So the attachment of this molecule to this molecule was the goal of the first reaction. And that had been successfully done in previous years with Dr. Krogstad. So that was relatively straightforward and easy to do. And this image in the next to the picture of the product is infrared spectroscopy, which shows peaks at different wave numbers. And then these peaks show different functional groups, which can be used to determine the overall structure of the molecule. So you can see this NO stretch shown by these peaks supports the production of this product. So you can reconstruct the product using IR. So IR was taken on this product and supported that we had created what we intended to. So the second reaction was using the product of the first reaction and trying to convert that NO2 into NH2, as you can see in these red circles. This was conducted using HSICl3, which sounds complex. And the reason we had to use this is, although this may seem like a simple reduction or changing NO2 into NH2, it's actually much more complicated. To create that molecule, you often use something called azide, which is 3 nitrogens linked together, and it's a very powerful reducing agent that could cause changes to our molecule in places we didn't want. So to combat this, we used HSICl3, which is a much easier method and safer to work with than N3, because that's a very dangerous molecule to use in the lab. Another reason we used it was because heavy metals, which are also used for reductions, we didn't want any heavy metals in our product, as this could possibly be a treatment for humans, and it also introduces possible issues with purifications. So we conducted this conversion of NO2 into NH2 using HSICl3. And although HSICl3 is safer than azide, it's still kind of dangerous to work with. During this whole process, all of the products had to be under complete nitrogen, so not touching the air at all. It was conducted in glass vessels that were under nitrogen flow, because nitrogen is a very unreactive gas, and many of the molecules we're using could become readily oxidized if they were exposed to the atmosphere, and that would cause changes that we didn't want in our molecule. So to use HSICl3 in the reaction, it had to be cannulaed, or this long metal tube that draws liquids from one vessel to another. And that was difficult because when you kind of took one end out and the HSICl3 touched the air, it kind of explodes, moderately explodes into sand in the air, which sounds dangerous, but I mean, it was kind of fun and it was really cool to see. And it also showed kind of the power of this reaction. And it was also cool to see because it worked. And when we got the IR, we had a great NH stretch here on this diagram. And that showed that we successfully converted the nitro group. And additionally, it kept the PTA characteristics we were looking for, which means we successfully made this molecule. And this is the first time this molecule has ever been made in recorded history, which was very cool to be able to do. And I really enjoyed that process. And this was kind of the reaction that was holding up the research in previous years. So to get that done was amazing. And then the next step was priming folate, which essentially makes the folate molecule more readily reacted. So it can react easier with the product of the previous reaction. So as you can see here, this is folate, this big chunk over here. And this is the product from the previous reaction. And this is the amide linkage I was talking about previously. This reaction was successfully done. It was not terribly difficult. The filtration was relatively difficult, but in the end, we were able to get a product and take an IR. It showed many of the characteristics that you look for in folate, as well as keeping that PTA characteristic and an amide linkage, which was great to see. And then in the final step, we were linking, so this product down here was supposed to be attached to cisplatin, which is in the middle here. It's that platinum core with 2 chlorines attached. Typically, cisplatin has NH3s right here on the bottom, but instead of that, we're attaching our PTA, kind of as the linker molecule. And this was done with COD, which is cyclooctadiene, attached to the PTA, and that was used because it readily comes off of the platinum molecule. And it also, cyclooctadiene smells horrible. And so when it comes off of the platinum, you can smell it. And it's one of the worst things I've ever smelled. But it is nice when you smell it, although it's horrible because it tells you the reaction worked. So that was also kind of one of those pros and cons things, but it worked. And then we took an IR of that product and saw characteristic peaks shown by cisplatin, and which was effectively demonstrating that we made our final product, which was great to see. And then some discussion. Obviously, this synthesis protocol was not done in one day. It was not done in one straight through reaction, onto the next, onto the next, onto the next. It took a lot of different strategies, changing amounts, solvents, which purification techniques, and overall we were able to narrow that down into a way that finally got us our final product, which was awesome. The first thing I kind of mentioned previously, the conversion of nitrobenzene into aniline, which was the NO2 into NH2, was successful, which was the reaction that was holding up this research in the past. Cisplatin and folate can be linked through PTA, which I mentioned. PTA was our linker molecule. Dr. Krogstad has worked with it in the past. It's great for attaching two different things to each other. So this demonstrated and supported that, this can be effectively used to link two different things together. Finally, the hypothesis was supported as infrared spectroscopy showed progressive functional group changes that we were looking for. Although infrared spectroscopy is a little harder and a little messier to read, we wanted to use NMR, but unfortunately, because of the COVID pandemic, we were unable to go to MSUM and do NMR on our products. But infrared spectroscopy still provided some good evidence that we were getting the changes we wanted. And this is an image of my final product. Might not look like a lot, but doing the synthesis protocol, you don't want to have a lot of waste, so doing this on a small scale is fine. And this is the filtration of my activated folate, which has a beautiful color, and you can see it's being held under nitrogen to keep it from reacting with air. And then in conclusion, this was an amazing project to get to work on. The getting to the end was really amazing. Being able to develop a protocol for something that could help people in the future is something that I really felt honored to do. Obviously, this protocol needs further replication and purification and different strategies to be used, but I believe it does have a good foundation and really could be used to help a lot of people in the future. It was amazing to get to see the chemistry in action and see the possible implications it could have for other people, even if it's a slight solution to help someone else get to the goal line. It was really amazing to do. I thank you so much for listening to my presentation. On April 14th, I'll have the Q&A if you have any questions or just want to talk about my research, what I enjoyed, a little more in-depth description of the protocol. I would love to talk to you, and I really appreciate you taking time out of your day to listen to my presentation. So thank you.